So it was fun and I enjoyed doing all this work. And then after that, I moved on to the Alfred Wegener Institute. I'd written some interesting papers, so I had built up my reputation. And I got this professorship here at the Alfred Wegener Institute. And then my field moved from Kiel Bight to the Antarctic, Southern Ocean. And there I worked in sea ice and also made some very interesting discoveries over there, also hands-on and under the microscope. And of course, it came out in the course of these studies, this was in the 80s, that the Southern Ocean was probably the swivel point for the global climate, for the climate cycles of the recent past, the glacial interglacials, right? That it was productivity of the Southern Ocean that was a steering element here. So when I started working in the Southern Ocean, it was really quite different to the Kiel Bight. And this is when, it took me a couple of years actually to figure it out. And this is because Kiel Bight is a very shallow sea, it's just 20 meters deep on average. And it is surrounded by land, it's an enclosed sea, and there's a lot of dirt in the water from the land. So the dirt contains iron, and we're living on an iron planet. 10% of the weight of the planet is supposed to be iron, the element iron. And Kiel Bight was saturated with iron, whereas the Southern Ocean, which is very far away from land and doesn't have any muddy sediments or anything like that, there was no iron. And at that time, of course, I didn't realize this difference, because iron was just like, it's given. It's there, it must be there, and so on. And all marine scientists start their careers in coastal water, where there's an abundance of iron. Like the North Sea also has a huge amount of iron available, but not in the Southern Ocean. So it took me, as I said, 5 or 6 years to understand that actually iron was regulating everything in the Southern Ocean. All the biology of the open Southern Ocean was run by the availability of iron. And that's when I then changed my view regarding the interactions between pelagic organisms meaning all those organisms that live in the water, plankton, but also the fish, the ones that live in the free water, away from the seafloor or from the land. Yeah, and then I did a couple of cruises with Polarstern, our research vessel of the Alfred Wegener Institute. Yeah, I joined the Alfred Wegener Institute and became a professor of biooceanography at the University of Bremen. And that's when I started then thinking about actually manipulating the ocean to avoid climate change. So this is the period when I started being exposed because of my interdisciplinary background, and here Alfred Wegener Institute. By the way, quite a few people from this special research project in which I was working also came here to Bremerhaven and so on. So we carried that whole thinking, that whole structure with us, brought it here. So I had close interaction with the biologists and the physicists. And then we started developing these ideas that we had to do something about it, about climate change. I realized early on, by looking at the carbon dioxide concentrations in the past and how they are now, for me, it was never a question of doubting anything with regard to climate change, because the evidence from the previous data and on today's data, the geologists' data, the cores they were taking from the seafloor and the cores from the ice, they were very unambiguous. It was very clear that we were headed for trouble, big trouble, really big trouble. And what I learned from my geologist colleagues, for instance, that in the last 15,000 years, okay, I have to mention this, the last 10,000 years have been very stable, exceptionally stable. And we've been very lucky that they've been so stable. So we think that the stability of the climate the last 10,000 years is normal, right? And if you have glaciers there, that's way back, and it's something different, and you don't relate to them. But in the period before the last 10,000 years, which is the Holocene, so the period before that, the 5,000 years before that, there were enormous changes taking place. Sea levels rose by 130 meters. So 50,000 years ago, that was the end of the Ice Age, sea levels were 130 meters lower than they are now. Imagine, 130 meters. And that ice melted in just 5,000 years. So if you calculate how much the rate of melt was per year, then there were periods in between where it was centimeters per year. Right? And we're going to get that. We're going to get that. It's going to happen. So I got into panic mode when I realized that what's awaiting us, and then we have to do something about it urgently. So one of the options was the iron fertilization, because this is where the carbon dioxide during the past had vanished. It had gone into the Southern Ocean. And the explanation is actually very simple, really. If you think in these terms, though, it's all understandable. The diatom bloom sinking out is like when trees in autumn shed their leaves. It's the same thing. You have a tree there and it's green. Okay, in the autumn it turns yellow. But then from one day to the next, you have a storm and they all sink out. And then they're all lying on the floor, see, on the forest floor. And similar things are happening in the ocean as well. But overall, the planet is greening. It's become more green. I can talk to you in detail about that as well, what that means and where that comes from. But we have more vegetation on the land now than we had, let's say, 20, 30, 40 years ago. And it's that extra vegetation which is burning, by the way. Those are the forest fires. They have increased because there's more stuff to burn. There's more fuel, vegetation on the land, which also shows you that the land itself is not a safe sink for carbon, because that carbon is going to be put back into the cycle, back into the atmosphere. We've had these drastic changes from a glacial climate, where I'm sitting now in northern Germany. There was a 3-kilometer thick ice shield sitting here, right? That extended from Scandinavia down here. So this was ice that was flowing south, right, up to the middle of Germany about. And that ice, and then North America was covered by ice also. From New York right across to California, there was an ice shield sitting in North America. And these two melted, and that's where we got the sea level rise, the 130 meters. And now we have Greenland, which is a remnant of that kind of ice shield, which is beginning to melt. And Greenland survived. It's an anomaly because it's 3,000 meters high. So the reason why it's not melting at the top is because the altitude is so high. But once that starts melting and the altitude comes down, it's going to speed up. And then we have had it. We're going to have a 6-meter sea level rise when that happens. So these are all the concerns that I had early on when I was introduced to this concept of glacial interglacials in the 70s and 80s, when all this stuff was coming out. And I realized what we were facing, and then I started thinking of emergency plans. What do we do to stop this from happening, apart from stopping emissions? And obvious that we have to stop emissions or reduce them drastically. But that's not going to solve the problem. And this is a misconception out there, which really bothers me, that people say, you stop emissions and think problem is solved. That's not true. The CO2 that we already have in the atmosphere is not going away. It's going to stay there. So whatever we are experiencing now in terms of climate change is going to stay there. And it's going to get worse because of the so-called hysteresis effect. You know, that the hysteresis effect is that the effects of a change take place slower than the change, right? So we are pumping CO2 into the air, that's going rapidly, but the effect of that lags behind. That's the hysteresis effect. So we're going to see more changes even if we were to freeze the current CO2 concentrations where they are. These changes are going to continue and get worse, although the CO2 concentrations remain the same. Now, what people don't realize is that the amount of CO2 that we have now in the air, 420 parts per million, we have not seen this for the last so many million years, many millions of years. And we are now crossing a watershed, a tipping point, which is going to take us into a completely different situation, completely different condition of the planet. And we just can't let that happen. So iron fertilization can do something, can help, but we have to remember that the cooling, the building of these ice sheets, the North American ice sheet and the European ice sheet, this took tens of thousands of years to build up, tens of thousands, right? The melt took place in 5,000 years, the big melt, 5,000, but to build it up took 50,000, right? So it takes much longer to build up the ice shields and cool the planet than it does to melt them. So we have a classic saw pattern, right? Long time building up, coming out of the warm period and entering the glacial period, the ice age, but then a rapid change transition to the next warm period. Daniel, what worries me, this is what makes me also so desperate, is that we might not have any more history after this. Once sea levels start rising, look at this year, it's been the hottest again on record. How much
52 degrees in India, where our main office is.
It's painful. Think of the people there. Not only the people, what about all the trees and plants that are left outside in that sea? They're going to start dying soon. There's going to be mass death. Right? Think of all the wild animals. Where are they going to go? All the birds and the animals and everything else, and the livestock and so on. There's going to be mass mortality. There's an upper limit. We are just at the upper limit of survivability for those organisms that are alive today. And this is so disturbing. And then once when sea level starts rising, then we are going to have so many refugees running around. There'll be no historians going to dig for that. They have to all look out to survive. So this is a tragedy of gargantuan proportions that we are going to be hit by if we don't really start reacting very soon. And right. Now, what we have to do is we have to convince people. We have to go to the people who are not biased and the younger generation, but they have been biased by their teachers, unfortunately, who are against all of this, right? I've had students who here at Bremen who had taken courses in one of these universities somewhere else. And when I talked about iron fertilization, they said, oh, how can you possibly do iron fertilization? They were told scare stories. Wow. I was shocked. But I know that this is what's happening. Right? So there's a lot of disinformation, I would say. No? Misinformation is when you go off the course, and when you tell lies, it's disinformation. And there's no proof for damage to anything. So if you say that it's happening, then it's disinformation.
That's what we're trying to fix. We're trying to give out information to everyone, and we're trying to educate people that are very active and very loud, like in Greenpeace, like in ETC Group. We're trying to give them the information they lack to form a new opinion.
Let's hope. I have climate anxiety, a high degree of climate anxiety, very high degree. And at the same time, also, I'm very concerned about all the other issues we have. Biodiversity loss, all the plants and animals that are going to go extinct as temperatures rise. And that drives me crazy. So I want to do my best. And iron fertilization, I want to give it my blessings, but it's not enough. But you know that story. The long term, for the really tens of gigatons per year removal of CO2, we have to do something else. It's something very...
Of course.
Yeah.
We have to decarbonize, and that should always be the...
not going to have... It's necessary, of course. We are on a sinking ship, right? And there's a leak. And that ship has already got a lot of water that has entered through that leak. And now we are saying, okay, we have to stop the leak, right? This is the emissions. Then the problem will be solved. That's not true. There's so much water in the ship that is already listing. The ship is already like that, right? And even if you stop the leak, then you've still had it. So how do you remove that water? You have to bail it out. And there's so many different ways of bailing the water out. You can get the passengers to carry buckets and throw it out. You can put a pipe in with a pump and pump the water out. But we have to do that. To get the ship back into some measure of thing, we have to do that.
the fascination about ocean iron fertilization, other ratios, and I can't emphasize this enough. We can buy for $10, maybe 20, maybe 50. Let's say the highest price we'll ever pay for a ton of iron sulfate is $100. And if we manage to figure out the logistics and the social license of being allowed to putting that ton of iron into the Southern Ocean, we can expect ratios of carbon sequestration, of biomass buildup in diatom biomass, if it's a silica-rich area of the Southern Ocean, of up to 50,000, you say. Maybe it's 40, maybe it's 30. And this is something, if we compare it to other methods of CDR, of carbon dioxide removal, most CDR methods have some kind of input for ocean alkalinity enhancement. You'd use alkaline material that binds with carbon. And most of these ratios are around 1:1, roughly, maybe. So the OIF ratio is 1 to 15,000 quantified and published in Nature, but it might be, if we measure it more over time and we have more data input, it might be 20, 30, 40, or 50,000. So you could say that the carbon capture ratio by photosynthesis, the initial carbon capture, that is safely 50,000 times higher than other CDR methods. And for a cost of, it just costs you, let's say, $50. So $50 bring you 50,000 tons of biomass, which is so fascinating for me. For me, this is like the most amazing fact about OIF, that you can get so much biomass. And from what I understand, at least in my research so far, I haven't found any other part in nature where there's photosynthesis and there's carbon capture and photosynthesis, and then that biomass is by itself sinking. So typically, like a tree is growing, and then at some point the tree is maybe dying and decomposing. Maybe a little bit of the carbon gets stored through the roots in the sediment, but typically the carbon is lost again at some point. And those diatoms, they grow on a huge scale, and then they sink and either become food for whales indirectly or remove carbon and cool down the planet. I guess the core question is, if we were to systematically fertilize the Southern Ocean, how much for, let's say, 1 ton of iron for $50, how many whales can we feed for $50? So how much whale biomass could we build up? And maybe how many penguins and maybe how many other animals? I guess you could create a model and quantify this in detail. I think science should. And then on the flip side, if we choose areas without any grazing, without any krill, basically what could be the carbon sequestration rate? Because in my math, if I'm assuming $100 per ton at a ratio of 15,000 in carbon export, if all of that carbon actually sinks down to the bottom of the ocean, we pay way less than $1 per ton of carbon removal. It might be 50 cents, it might be 10 cents, it might be even lower. And then if we target areas of the ocean on purpose that help us to grow krill biomass, obviously that rate is lower. And maybe that's a good thing, because we want more whales. We also want, let's say we do OIF for the sake of tourists and for the sake of fisheries, and we want everyone to, not only the climate problem to be addressed, we also want the fish problem to be addressed. So then maybe the ton per carbon is maybe $5 per ton, because the rest gets built up in whale biomass. And from what I understand now, I'm reading your presentation, it really depends which area you pick, right? It's the krill area, and it really depends what diatom species are already dominant in specific areas.
Of course, that is something which once we start this thing, you have to fine tune and find out.
Just for our audience, to put that into perspective, the entire carbon removal industry combined removes around 50,000 tons per year currently. Mm-hmm. Maybe this year they will grow to 100,000 tons, but no one in the carbon removal industry has any credible path towards a gigaton or even 100 million tons at prices that are affordable. So The fascinating thing about ocean iron fertilization, and even if we do not have gigaton potential in certain areas outside of the Southern Ocean, is it's still millions of tons at very low prices relative to building out direct air capture plants or to trying to bury biomass onshore and all these other techniques that you've also went through in your lecture.
Is that it got a lot of coverage. I think it was published in Nature, but it's not cited by the people who were looking at iron fertilization experiments because theirs didn't function. So they give iron fertilization experiments a bad name, like it doesn't function, that carbon doesn't sink out of phytoplankton blooms, because either it was too short, that two-week experiment, low Isonex was 3 weeks, nothing sank out. So we cannot reach any conclusions because it didn't sink out. But if you stayed one more week, it would have sunk out. My colleagues are like that. They are defensive when it comes to carbon dioxide removal. They prefer not to have it because they want us to reduce emissions before taking anything out. And I see it's a defeatist position because we have to take carbon dioxide out because the carbon dioxide we have now is not going anywhere. It's going to stay there. So even if we stop emissions right now, this moment, whatever we are seeing in terms of disasters, climate disasters, are going to continue. So we have to at least develop the methods, the technology to remove the stuff. And the earlier we start, the better. So we've lost all this time by people avoiding, right? So they just don't cite, and then it's finished. And then somebody else said, yeah, in an eddy, those particles get sucked down. Somebody said that once. And it's ridiculous. You saw the experiment. There's nothing being sucked down. Now, because this is the first time that we could show that an eddy, a rotating eddy at the surface, is also rotating at depth. This is new for the oceanographers. And we could also prove that because we put buoys in that went down to 1,000 meters and then came up, like the Argus floats. You heard of Argus floats? These are buoys which you deploy in the ocean. There are thousands of them now in the ocean. Because when they are at depth, they cannot send any signals because the water column is opaque to any kind of electromagnetic radiation. So you can't send any radio signals. Light also is absorbed quickly. So you can't do anything. So these buoys have to come to the surface and then send the message and then go down again. So they have to be pre-programmed.